Welcome to Data Brew by Databricks with Denny and Brooke. The series allows us to explore various topics in the data and AI community. Whether we're talking about data engineering or data science, we will interview subject matter experts to dive deeper into these topics. And while we're at it, we'll be enjoying our morning brew. My name is Denny Lee. I'm a developer advocate here at Databricks and one of the co-hosts of Data Brew.
And hello, everyone. My name is Brooke Wenig, the other co-host of Data Brew and machine learning practice lead at Databricks. Today, I have the pleasure of introducing my advisor, Ameet Talwalkar, to Data Brew. Ameet is the chief scientist at Determine AI and assistant professor at CMU University. Welcome, Ameet.
Thanks. Great to be here.
All right. So I know you have a very long history in the field of machine learning, but I want to rewind it a bit. What got you into the field of machine learning?
Yeah, so it was a pretty long and windy and kind of random walk. I guess starting even with, at an early age, I was always really excited about math and maybe also biology, I would say. In college, I started as an econ major. I ended up stumbling into computer science. Didn't really think I would do anything in computer science after college. I had a few different jobs right out of college. Largely, I was playing a lot of Ultimate Frisbee. But at one point, I stumbled into working in a neuroscience lab, and I both realized I was really interested in sort of how the brain works and just understanding the details of how the brain works. But I also wanted to do something mathier, and I sort of then again stumbled into grad school and discovered machine learning, which was to some extent I think satisfying that criteria. Very much more mathy. Depending on who you talk to in machine learning, it's to some extent motivated by the brain or not, but it is somehow trying to use data to make predictions and somehow related to intelligence. Again, depending on who you talk to. But to summarize again, I've always been really excited about math. I discovered an interest in computer science before it was cool, and then I also stumbled my way into machine learning again well before it was cool. Right, I started grad school in the mid-2000s, living in New York City. All my friends were working in finance. I loved what I was doing, but nobody else seemed to be all that interested in what I was doing, which is a night and day difference between then and now. Not just with me, but with the field, obviously. So that's been interesting.
Yeah, I stumbled into the field of computer science once it was already pretty cool. This was back in 2012, and Amit's actually the main reason why I got into the field of machine learning. I was taking an online course. This was way back when Databricks had these online courses that they ran through edX on distributed machine learning in Spark. And I saw that Amit was teaching the course when I was interning at Splunk trying to use Spark there. And I reached out to Amit and said, like, hey, can I take your class in the fall? He said, yeah, no problem. So that was how I got into the field of machine learning, was through Amit. And then he ended up being my advisor.
Yeah, Brooke was great to work with. And your Chinese was also, every day she would surprise me with something new. She's fluent in a bunch of languages. She's brilliant. She asks a lot of great questions. And I guess we're going to talk a little bit more about interpretability later, but it's kind of funny because a project that you worked on a little bit with us related to decision trees was also a project that we then kind of morphed into our first work in interpretability back in 2017, 2018. So kind of all comes full circle, I would say, a little bit. Yeah.
Well, thank you for the kind words. I think this is actually a really nice transition into what are you currently working on? What are your current research areas of interest, and how have they shifted over time?
Yeah, so I think, from the time I started in grad school, soon afterwards, I spent a lot of my time interning at Google Research in New York City. And it just felt like there was a disconnect a little bit at that time, for me at least, between the field of machine learning and academics versus how people were starting to be interested in it in industry, in the sense that it felt like maybe not the biggest problem, but a big problem and opportunity for machine learning back in 2008, I felt, was kind of getting it out the door, right? It was very complicated, very mathy. It sort of seemed like you needed a PhD in computer science or statistics or math to have any hope of actually using these sorts of methods. But at that point, at least at places like Google, data was already becoming, the most important thing to them. There seemed to be a lot of opportunity to, take advantage of this data and use machine learning and other sorts of predictive tools. And it felt like, getting it out the door was the real problem. And so I would say, to answer your question of what I'm working on now or how has it changed, I'd say that starting as early as 2008, 2009, my interest has been in sort of getting machine learning out the door. I also call that democratizing machine learning, but really coming up with principled tools that allow people to use machine learning either more easily or at this point maybe more safely. But that, so that has been kind of the underlying motivation for my work for the last decade or so. It started, to me, a big question or a big challenge, and this wasn't just for me, it was in the field, was one of the scale of data back in the late 2000s and early 2010s. And that's what led me to be interested in distributed computing and Spark in particular. So I worked, after my PhD, I went to Berkeley for a postdoc, and that was, working in the AMP lab right when Spark was starting to take off. So I worked, side by side with other folks working on Spark, and also side by side with systems people, coming from a much more ML background. And it was just super interesting, and it remains that way for me today to work with people kind of from different backgrounds in terms of, right, if you work with, I found working in machine learning with, other machine learning researchers, we would all ask, obviously they're very, very smart people, but we kind of all had all of the same context. So sometimes we wouldn't ask the basic questions, we'd immediately go to the really technical questions. You talk to people who are a little further away, they would ask seemingly the really simple basic questions, but in some way they're the most piercing questions because they question underlying assumptions that other people in your very small field, all for better or worse, take for granted. Anyway, so yeah, I guess going back to your broad question, the way my work has changed over time has been in terms of what I think are the most pressing problems, or some of the more interesting and emerging problems in terms of getting machine learning out the door or making it, democratizing it. And I'd say specifically the three sets of problems I've worked on over time. First, focus on scale, parallelism, scalability, and that's working in the AMP lab, working on Spark, working with those folks has been super amazing and fun. The kind of second stage for me, and obviously it wasn't so disjoint; these things were all overlapping. The second set of things I worked on were related to automation. And I think Liam came on your podcast at one point and talked about some of the stuff that we worked on together there. And more recently, and again, I think scalability and automation are still really, really fundamental bottlenecks and super important, obviously. But a lot of work that I've been thinking about, or a lot of research and problems I've been thinking about recently, have been moving more towards this notion of safety. So now people are using machine learning more due to things like Spark and TensorFlow and PyTorch and just the general society becoming more educated on machine learning and deep learning. So people are using it more and more, which is great, but it's also kind of scary because people can be using it in the wrong way. It's sort of terrifying in some sense. So, people who are already using it today might not be using it safely. The people who are going to be wanting to use machine learning in the future are likely going to be, potentially less and less sort of experts in these different fields, right? It's going to be undergrads who are AI majors from Berkeley or CMU rather than PhDs from those places. And we need to make these tools easier and safer for people to use. And I think interpretability is a really important part of the safety equation. So I don't know if that answers your question or partly answers your question.
I think it definitely doesn't, but I'm actually going to go do a bit of a retrospective back because you covered a lot. Okay. So first things first, the most important question, do you still play Ultimate Frisbee?
I throw the Frisbee a little bit, but I've torn my ACL more than once. So, Brick knows I like biking more. Part of the reason I like biking a lot is because it's much nicer on your knees. So I miss that a little bit in Pittsburgh because the hills aren't quite the same as what they are in California. Neither is the weather. The weather is also a little different, but I play a little bit of Ultimate, but much less than I used to for knee reasons.
Okay, so do what I do, which is you bike so you can play Ultimate. That's the key thing here, right? So, okay, back to the real questions. My apologies, but I had to segue off. You started off talking about exactly like in your 3 points in the evolution of your history, like from scale, automation to safety. Okay, so let's start a little bit on the scale automation part for those who may not have actually heard Liam's podcast yet. Like, how did working with machine learning within the context of a distributed computing environment like the Spark project allow you to scale? Like, what were you trying to address at that time? Because for a lot of folks, they might not actually have that historical context.
Yeah, I mean, back in the day, and I think this is still true, right? The broad thing you're trying to do with machine learning is to use data to kind of, try to learn from the data that you have and learn underlying patterns in your data. And the general rule of thumb is that more data is better, right? The more data you have, the stronger the signals in your data are going to be. Maybe the more nuanced the signals and the patterns that you're potentially able to learn. So on one hand, data is the underlying, is the underlying currency. It's a thing that allows you to, that potentially will allow you to do what you want it to do, or allow you to do what you want to do. But the problem is that classical machine learning methods and statistical methods were really, proposed and studied largely from a statistical and learning theory perspective, right? They weren't, right? These methods were developed at a time when we didn't have that much data. We had 100 points or 1,000 data points, and everything could fit on, your laptop running in MATLAB or R. And so the real focus was on statistical problems, and those again have not gone away. Those are super interesting, obviously, and super important. But there was a real lack of people thinking about how to take, let's say something like an SVM. Kernel methods were king in the 2000s. So you take something like a kernel method, which was motivated for a bunch of reasons, but now all of a sudden, let's say you want to, you want to train your SVM and set them on 100 points or 1,000 points on 20 million points, right? And this is a problem that I worked on at, before starting at Berkeley when I was at Google or at NYU and Google. And even storing a kernel matrix that's 20 million by 20 million, the details here don't matter, but storing a dense 20 million by 20 million matrix is just a super hard thing to do from a storage point of view on one machine, let alone on a bunch of machines, right? And so that's just one example, but even for large linear models or random forests or decision trees or whatever sort of models that you're thinking about, on one hand, there's this tension between wanting more data to train better models and the underlying computational and storage concerns associated with actually trying to run efficient algorithms to actually train these models. And so something like Spark or distributed computing is as we all know really powerful and nice in terms of it allows you to get access to much more storage and computation, but it also leads to new complications in terms of how do you have these different parallel workers communicating with each other, right? And of course, Spark provides a really nice API and programming model to allow you to do this, but you still need to come up with the underlying algorithms that that work under the MapReduce or the Spark sort of paradigm. And especially in the 2010s, once I started at Berkeley, that was a lot of what I was thinking about, while also learning a lot about distributed computing and about Spark and so on, right? So I in theory was working on distributed machine learning during grad school, but I was doing it with just other ML people and theory people, and I knew next to nothing about systems. So I was thinking a very simple, naive, divide and conquer methods, implementing everything in MATLAB. Moving to Berkeley, working with systems people allowed me to think about this in a more robust sort of way, which was, super interesting for me.
I completely get you. That's in my past. That's exactly what I did. Basically, could I shove everything into a gigantic MATLAB server and hope the heck it would actually not blow up in the process? So actually, I did segue a little bit more into our actual topic about interpretability, but you did mention something that's sort of important, which is about how to work with models more safely. Right. And so can you provide maybe some examples of what you mean by like not working with machine learning models, examples of machine learning models that are not safe, like how we're not using them safely?
Yeah. I mean, I feel like we hear horror stories. And to be clear, I think there's more questions right now than there are answers in this area, which is why I think it's an interesting set of research problems. But, I think there's probably a lot of examples. Two really, really natural ones, I think, are one related to privacy, right? So our data is being collected by a bunch of different organizations. In some cases we know about it, some cases we don't. But obviously there's some private information probably in some of the data that is being collected on us. And there's a question to what extent these models, A, are using our data, and B, if they are using our data, to what extent is it revealing private information about ourselves, right? And so there's a lot of work, growing work in the field of machine learning on privacy. Federated learning is an example of this, of keeping your data local, so that, to some extent it's motivated by mitigating privacy. Differential privacy has become a topic people think a fair bit about. But, one way to not be safe is to have models that are trained on some data, that data somehow revealing sensitive information about the people or the organizations or whatever sensitive information it's revealing, whatever sensitive information is in that underlying data. So that's one. And then, the other obvious thing that people talk about is fairness or lack thereof, right? So at one point, there was this thought that machine learning could be this beautiful solution to, get rid of human bias, because the models, machine learning isn't biased itself. It's just learning patterns, right? And that's a nice idea, but what machine learning is really doing is learning patterns in data that you've collected and in many cases amplifying biases that already exist in your underlying data itself. And we all know that the way our data is collected is often in a very biased fashion, right? And there's huge numbers of examples of this. But right, so the point is that using machine learning can really give you a false sense of being unbiased, when in fact what it's often doing is propagating existing biases in data, and doing it in a way that it's people call it like what was it it's like there's an analogy, there's a cute phrase for it, but I can't remember. But it's like equivalent to money laundering, like data laundering or bias laundering, right? That's what people call it, right? So not only is there bias in machine learning models, but you can imagine doing it in subtle ways that people might not. I mean, at this point, I think people know that this is a major problem. But I think those are two real safety concerns. You could potentially argue that there's other safety concerns related to just deployment. In terms of is this draining the battery in my car or my cell phone or something like that. But generally, when I think about safety, I'm thinking about largely privacy and sort of fairness concerns.
So why do you think there's so much emphasis on the field of privacy and fairness now compared to like 5 years ago? Is it because there's more use cases, more people working in machine learning? Just want to get your thoughts as to why there's more emphasis now.
I think it's the first thing you said. People are actually using machine learning. It's actually influencing our lives a lot. And if you look at the trend of 10 years ago, nobody cared about machine learning other than machine learning researchers. Now it's just incredible. It's probably overhyped and people are talking about it too much. But there's a reason people are so excited about it. It's actually, we've seen a bunch of transformational applications powered by machine learning, and there's a real thought that it's kind of just tip of the iceberg. So for every application or every organization that's using machine learning today, you expect there to be orders of magnitude tomorrow. And so if we're already seeing bias and fairness and privacy problems manifesting today, those are just going to get worse and worse over time as people are predicting more and more people are using machine learning.
Got it. Well, I think this is an excellent segue into the paper you recently published titled Towards Connecting Use Cases and Methods in Interpretable Machine Learning, because you talk a lot about this disconnect between use cases and methods and machine learning interpretability. Could you walk us through some of the key tenets that you address in that paper?
Yeah, sure. And I should start by saying, the credit goes to my students here. So Valerie, Jeff, Greg, and June, they did a lot of the hard work here, all of the hard work here. And the story behind this paper was largely just us thinking about what we think are the, important next steps and the current problems in the field of interpretability. And I think a lot of what we were saying is, a lot of it is not new, and a lot of it is hopefully things that people already know, but hopefully it's packaged in a way that is accessible to people who are new in the field, and kind of it's a modern take on problems that people have already kind of known about. But the core idea behind the paper is just that, right, ultimately interpretability, the field of interpretable machine learning is, meant to be creating a set of methods that people can use in practice, right? But there's really a huge disconnect right now between the researchers who are studying this problem and coming up with new methods, and practitioners who are using machine learning and saying that they want interpretable, they want to understand their models, right? And this disconnect is really, I think, a real bottleneck in the field right now. So, and I think an underlying reason why there is this huge disconnect is that the idea of interpretability is kind of inherently squishy, right? Like, what does it mean for something to be interpretable? It's not an obvious thing to define. We had a reading group back at CMU, I think maybe 3 years ago now, about this, where we were just reading about, at that time, what the kind of main papers were in interpretability, the main works, and different ideas. One week we had one of the people in that reading group was a PhD in English, which I was surprised about, but he was able to keep up. But we asked him to present one week, and he presented on various ideas a psychology perspective on interpretability. And sure enough, right? Well, again, I'm no expert in psychology, but my vague recollection of what we talked about was in that group meeting, or that reading group, was that even in the field of psychology, they've thought about what interpretability means from just a psychology human perspective, and unfortunately, there's no one clear answer, right? So if psychologists have been thinking about formally trying to define interpretability for decades and haven't converged on yet one answer, maybe it's it's unlikely for we in the machine learning community or computer science community to solve that problem in a matter of a few years. But right, so the fundamental problem is that there are researchers developing new methods for what they think the problems are in interpretable ML. And then there's practitioners who are using, say, neural networks and trying to understand what these models are doing. And these two communities want to be working with each other, but are not. And they really could help each other, but they're not. And what that means is that, right, people are kind of, and again, I know people aren't doing this, to be malicious or anything, but a lot of research in the interpretable ML community is focused on problems that may or may not actually be problems that anyone cares about, right? So people are coming up with abstract problems saying that this is an interpretability question, but there's no real motivating application for it. It's really hard to even evaluate whether their methods are even working. And so they write this nice paper. They're cool ideas. Maybe there's nice visuals of different neurons in a neural network lighting up, or whatever. But that's never going to translate to somebody actually using this stuff in practice, because we don't really understand what practitioners want. Similarly, these practitioners, they want to understand their models, but they might not know enough about ML to be able to formulate, quantitative, mathematically precise questions that researchers can actually answer themselves. And so, right. So the point of his paper was to further highlight this problem. And again, other people have talked about this before, but sadly, this, I think, still remains a really, really big bottleneck in the field. And a related bottleneck is, how do you evaluate the quality of any new interpretability method that you're coming up with? Any evaluation needs to be somehow, based on a real application or motivated in some way as a proxy for performance in a real application. And if we don't know what these end-to-end pipelines look like and how a method's actually going to be used in practice, it's just really hard to even know what problem to be solving. And so the point of the paper wasn't just to be negative. It was to say, hey, this is a problem. This is what we do know. And it was kind of a taxonomy, proposing a taxonomy, organizing the information we do know about different types of methods, and focusing on what I would argue is the quote unquote easiest interpretability problem for practitioners, which is model debugging, which is still not an easy problem at all, but it's relatively easier than, having a doctor trust your machine learning model. That's orders of magnitude even harder. I don't know how to solve that problem. But I think model debugging maybe is a problem we could hope to try to solve with data scientists working in collaboration with ML researchers to, ground the research in real problems and to do end-to-end evaluations ending, in actual applications. Anyway, so that was a very long summary of what we talked about. Hopefully that makes some sense, but I'll stop.
Yeah, that definitely makes sense. And so in the paper, there are 3 key tenets: problem definition, method selection, and method evaluation. The one that resonated the most with me was the problem definition, because I see this with all of our customers whenever we're trying to scope engagements of what is it you're actually trying to solve. They'll often say, like, I want the model with the best accuracy. I'm like, all right, are you trying to optimize for accuracy? Do you care more about false positives, false negatives? There's often a lot of disconnect between the business side and the machine learning engineers or the data scientists. So this paper definitely resonated with me from that perspective.
Yeah, and I think our proposal in the paper is very similar to what you said, and there's no easy answer there. You have to talk to each other, right? Like, there's no way me as a researcher, I can just say this is the interpretability problem people care about. I need to talk to people in the field who actually have these problems, try to understand their applications and their problems well enough such that I can then, translate that or abstract that problem into something maybe more formal and mathematical, and then try to solve it. And kind of a big argument that we make in the paper is that that sort of process needs to be happening over and over again. So researchers need to be like, reaching across the aisle to talk to practitioners and vice versa. And we need to be solving these problems together over and over again, such that we get more abstract problems that are actually grounded in reality. And I think that's it's fun. It'll be fun and interesting to do. And, we're starting to do that in my group as well, to learn and figure out what are the most interesting problems to solve. But I think there's a lot left to do there.
Right. I was actually hoping you would provide an answer that said, well, now I don't have to talk to anybody because we're doing all this on computers. But I guess that's not the case.
Yeah. I mean, that was sort of a concern that I had starting in interpretability, was related, like, when we started working in interpretability, the way people evaluated their results were user studies. And I was really nervous about running user studies because it just felt like that was not an area of expertise for me. I didn't know if I trusted the results so much. I don't think user studies are the be all end all, but I think, user studies in the sense of like using mechanical Turkers to evaluate the quality of your, I think you actually need something deeper with user studies, which is you actually work with practitioners to understand their problems, which is even more time consuming than running a a mechanical Turk experiment, but I think potentially way more rewarding as well.
No, it makes sense. I mean, in some ways, it almost segues or reminds me of like the idea of like the theoretical statistician versus the applied statistician. The fact that you actually needed both in order to be able to one that could still do the mathematics behind everything, while one that actually started figuring out, oh well, how is it actually being applied and how to actually connect with everybody that's around.
Yeah, and it's not clear to me that this is going to need to happen forever, right? Like the analogy that I make is that you know we can abstract problems in machine learning like clustering or binary classification or regression because we know that there are enough practical applications that roughly fit those APIs such that you then can have practitioners and researchers maybe be a little bit more removed from each other. Or hyperparameter tuning is another example of that. But I don't think we've established those APIs yet in interpretability. I don't think that there's an infinite number of problems and every interpretability problem is a bespoke problem. But I think we need to figure out what are the, K different canonical interpretability problems and what are, how do I formalize those mathematically? How do I evaluate them the right way? What are the canonical examples of real applications for each of those to kind of, to make this more of a formal and rigorous sort of field? And I think that will happen. It kind of needs to happen, but we're not really there yet.
No, that's fair. And I think look, going back to your definition about like there's no one clear answer for interpretability, right? So then I'm wondering if that it's because related to privacy and fairness. That's why there's this massive need for transparency, so you can actually figure out what the heck's going on. I'm just like from your perspective, yeah.
I guess we haven't bridged those ideas yet, right? If what we care about is sort of fairness and privacy, maybe where does interpretability even come in? And I think the argument is that if we know these models are going to be flawed in some way, we need to be able to poke around and inspect them and evaluate them and check that they're doing reasonable things. And that I think is where interpretability comes in to, can I use interpretability to evaluate whether something is biased and maybe then fix that bias, or similarly privacy or something like that. So I think, if we knew a priori that our models were perfect, then maybe we wouldn't care what they were doing and we wouldn't need to inspect them. We wouldn't need them to be transparent in any way. But obviously that's not where we are now and probably will never be where we are. And so we need to understand, what they're doing and we need to be able to evaluate them.
So in terms of understanding models like neural networks, I know LIME, SHAP, integrated gradients are very popular. What are some of the pros of these approaches and what are some of their shortcomings? And we still need to be looking forward to solutions in the research field.
Yeah, I mean, great question, right? And I think that all of those methods are really interesting. They're, in some sense simple, but I think in a good way, right? Like in retrospect, I think, they're natural starting points for what you might want to do. I think the real disconnect, there's nothing wrong with their methods, but they're all solving different fundamental mathematical problems, right? And they're all well-specified problems. There's nothing, but in the same way that, if fundamentally what I care about is, if I make the analogy to different types of machine learning problems, if I want to solve a binary classification problem versus a clustering problem, I might use a different method. Right now, people don't even realize that, LIME, SHAP, and integrated gradients are solving different problems. And so what you often see is that people just say, okay, my problem is an interpretability problem. SHAP has really great open source software. So Scott Lumber, the first author of that work, he and his colleagues did a lot of work to make those methods accessible to people. And so people use them, but they sometimes use them the right way, and they often, though, sometimes use them the wrong way. That's not an issue with the method. Every method has strengths and weaknesses, or every method was intended for certain things, but also not intended for other things. And so I think having people understand when these methods are applicable and not applicable is kind of the issue with all of them. And it's true with any new method that's going to be proposed as well. It's not really an issue with any one method as much as people understanding the taxonomy of these methods and knowing how to evaluate each of them for their specific problem to know whether it's the right method or the wrong method.
Got it. So then, I mean, I actually want to sort of bring it back to your paper, actually. And the real quick call out that I noticed is that in the work of the paper itself, right, is that you synthesize a foundational work on IML methods for evaluation into an actionable taxonomy, right? So I'm going to ask the question, from more of a naive perspective, because that's where I'm coming from, right? Which is, could you explain that? Like, what is the context in terms of now these new methods for evaluation and the taxonomy that goes with it?
Yeah, so there's where the taxonomy is today and where we want a taxonomy to ultimately exist. And so, in an ideal world, a taxonomy would exist where, it's you can either start from it at the top or the bottom, right? So if you start from the top, you're a user, and as a user, you say, okay, let's say you care about model debugging, right? Well, so as a user, you might first say, what do I care about? Why do I care about interpretability? Am I a developer of models, and do I want to debug the model, or do I care about trust, or do I care about something else, right? And then if you say, right, I care about model debugging, then there's questions about details about the specific problem that you care about, in terms of like not all model debugging problems are the same. There's maybe different types of model debugging problems. So one part of the taxonomy, and this is the part that we know less about, is going from broadly saying I care about interpretability to actually specifying a specific, well-specified technical mathematical problem that needs to be solved. And so that's similar to saying I want to use machine learning to I want to solve a binary classification problem. So that's one part of a taxonomy. That's the part that kind of doesn't exist yet today. The other end of the spectrum is, if you're a machine learning researcher, you start with your particular method that you've solved. Your method is solving some technical objective, which is in some way motivated by broadly interpretability, but then different technical objectives or methods from different technical objectives, and it's not really a one-to-one thing, but methods solving different underlying objectives can be used to solve one or more well-specified use cases, say a well-specified model debugging use case or so on. And so the dream would be that we work through enough of these end-to-end use cases together, researchers and practitioners, such that over time we can build on these individual use cases to flesh out this taxonomy, such that in the future people can say, I want to come up with a new method. I think that this particular type of use case could use better methods, right? And I know how to, this use case is well defined in an abstract sense, along with data sets and problems to do evaluation for that use case. So I, as a researcher, really don't have to now go end to end anymore. I can just use benchmarking data sets, benchmarking evaluation metrics, and just solve the technical interpretability subproblem associated with that use case. That's where we want to go. Where we are right now is some pieces of that taxonomy are better understood than others. And I would also say that, my group and I writing this paper, we're much more coming from the IML researcher point of view. So we understand the bottom part of that taxonomy better as well. And I think that a big contribution of this paper was at least providing down our take on how the taxonomy looks in terms of different types of methods and different technical objectives that they're solving. We know less about all the different practical use cases of interpretability. That's what we're trying to educate ourselves on right now by working with other people. But we also think that this kind of shared vocabulary talking about this problem generally will hopefully allow not just us, but other people to start fleshing out the clear gaps that currently exist today.
So speaking of the field of machine learning research, what advice do you have for people that want to get into this field? I know you did a PhD in kind of the more traditional route, but what advice do you have for other people that might currently be in industry to get more involved with machine learning research and interpretable machine learning?
Yeah, I mean, I think it's a great time to be in this field, whether you're in academia or industry or whatever. Right? ML is just increasingly pervasive, increasingly important practically. I think it's only going to get more and more important over time. So I think it's a great time to get in. It's very exciting. I think that what I would recommend anyone to do is to learn a little bit of math. Right now, I tell people that I get more theoretical every year as a researcher, and it's not necessarily because my research is changing, but it's because when I started grad school, machine learning was to a large extent, a field of applied math, right? And I wanted it to be more. My interests were kind of more at the intersection of theory meets applications or theory meets practice, when the field was very, very theoretical. The field is shifting more and more to being an applied sort of, applied, coming up with systems, using it in practice, which is great. But that doesn't mean the math isn't important. So if I have one piece of advice, it's learn, no matter what you're doing, don't be scared by math and learn the underlying math. That's the underlying statistics, linear algebra, and optimization maybe, and calculus that you need to, and more, all of this stuff there's amazing tutorials online, whether it's in the form of MOOCs or whatever else, blogs. So this material is all available somewhere for people to read. I would highly recommend people learning math. So that's one. Two, I would say don't be distracted by the hype, right? So machine learning is increasingly important. I don't think that, by no means do I think that everything that's going on now is just a bubble or hype by any means. That said, there is a lot of hype in this general field. And, I would say that people who are interested in working in this area should be working on interesting problems that are potentially solving, important high impact areas, not just what's the flavor of the day today because it's hyped up by, whoever is hyping it up. So maybe those would be my two big pieces of advice. Three pieces of advice. Do it because machine learning is great. While you're doing it, learn math. And three, don't be distracted by the hype, but instead pick interesting problems, even if they don't seem to be the coolest problems today. Because what's in vogue today might not be in vogue tomorrow, and things are pretty cyclical. So
that's some super helpful advice. I still remember in grad school having to go back and relearn all of the linear algebra, stats, and calculus that I learned in undergrad because I was like, when do I ever care about taking the second derivative of something? It's like, oh yeah, if it's a convex function, I'm going to want to do that all the time. So yeah, I definitely like that theme of learn math and don't be distracted by the hype. As someone who works in industry, there are so many advancements coming out, both from industry and academia. I'm like, all right, what's the latest flavor of the day, as you'd said, of object detection or image classification? But I think the overall theme of solve an interesting problem with high impact is the best advice that you can give.
Right, and it's often the case, right? And it's not at all to say that the latest research coming out isn't interesting or couldn't potentially be high impact, but it is often the case that when you want to, it's almost always the case that when you want to solve a problem, you should start with simpler methods, right? And only when those simpler methods don't work do you try to use more and more fancy things.
Definitely. Well, I want to thank you again for joining us today on Data Brew and sharing all of your expertise about interpretable machine learning and advice for getting people into the field of machine learning research.
Great. Yeah, it was really great to get to chat with you guys. And thanks for having me.